In this segment we will study Laplace's equation in two dimension. Our main aim is to solve numerically the continuum Laplace equation, but we cannot solve continuum equation in computer. First we have to convert our continuum Laplace equation, which is del 2u del x2 del 2u del y2 equals to 0, into a finite difference form. As we know, the second order derivatives are represented by central difference approximation as del 2u del x2 is u x plus dxy minus 2u xy plus ux minus dxy delta x square, and similarly del 2u del y2 as this identical formula but in y variable. Therefore, if we putting the values of this finite difference form into our equation 2.1, we will straightforwardly get this equation, which is this thing is here this way and this thing is this. And in order to solve in computer or numerically, I have to first consider a rectangular grid with dimension Lx and Ly with u specified on the boundaries. If we specify u on the boundaries, that is called the Dirichlet boundary conditions, and now we construct a grid on which we will determine u's at the points xi equals to I delta x, where I runs from 0 to nx and yj equals to j times delta y, j equals to 0 to ny, with delta x equals to Lx by nx plus 1 and delta y equals to Lx divided by ny plus 1. For simplicity, we choose del y equals to del x. Therefore, this del yx and these things will cancel out, and this equation will be very simplified into this 2u and 2u will be added, and all these things will be represented in a very cleaner fashion in this way. Uxy equals to uij, ux plus delta x comma y equals to ui plus 1j, ux minus delta xy equals to ui minus 1j, ux comma y minus delta y equals to uij minus 1, ux y plus delta y equals to uij plus 1. And therefore our this two finite difference form will be casted as ui plus 1j, ui minus 1j, uij plus 1, uij minus 1 minus 4 uij equals to 0. And this is our main equation. Uij equals to 1/4 of ui plus 1j, I plus 1 comma j, ui minus 1 comma j, ui j plus 1, ui j minus 1. That means if we concentrate on these points, therefore ui plus 1j means this point, and ui minus 1j means this point, and uij plus 1, that means in the upper direction this point, and uij minus 1 is this point. That means whenever we calculating the value of ijth point, that means 4 nearest neighbor values are required to compute at the particular node. That means it is a kind of a stencil kind of thing. That means whenever you calculate the value at this point, we need the 4 values at the neighbor, 4 values at the neighbor. Okay, and here we compute basically all the interior points. That means u11, u21, u31, u12, u22, u32, u13, u23 and u3. This is a very small grid, all these points, because the red boundaries are given from the Dirichlet type boundary conditions that you know from the Dirichlet boundary conditions. And here we have writing these things. u0j, 0j means 0 means x-axis 0 and j is running, that means this is this axis, and ui and unj equals to b. nj means another direction, it is the left boundary condition. You can say this left boundary condition, it is your right boundary conditions. This is your right boundary condition, these things. unj equals to b. Yes, j is running, and ui comma 0, y is 0, I is running, that means x axis is running, that is this thing, this is your c, and uid, this is basically bottom boundary condition, bb bottom boundary conditions, and top boundary condition in, which is basically d, which is given. From there we have to compute all these interior points u1, 1, 2, u3, 3, all u's. There are several methods for solving this. Iterative methods are there. One is very simple method, Jacobi iteration. Another is Gauss-Seidel iteration, and another is successive over or under relaxation technique. First, in this segment or in this episode, we will just concentrate on the Jacobi iteration. And look at the figure 2.1. That means this figure. All the boundaries are mentioned here, as we already told you. These are the boundaries are given. Our task is to compute u11, u21, u31, u12, u1, this is the next values, some typos, and these are the interior points, and we assume all the interior points are initialized with 0 value. That is, all the interior values are initialized with 0 first. In computer we will first initialize with 0 value. That means all these interior values are initialized with 0 and with given boundary conditions. Now our first aim is to calculate in the first iteration we must turn our turn to start our iteration from the bottom left position. That means this position. From this position, whenever you calculate u11, this value is given, this value is given, and this value is given, this value is given. This is 0, 0 initially, and this value are given from the boundary condition. You compute this value. Something is computed, and then you go to the next point u21, and you know only you need 4 values in the neighbor, this one, and this one. Now you are left with the new u11 value, but you don't use the new u11 values. In Jacobi iteration, you use the old u11 values whenever you are running the particular iteration. So in the first iteration, u11 is computed, but we do not use while computing u21. So u21 will be calculated previous value of u11 and the current and the boundary value and these values and these values. You compute this value. Now you go to 3 1 1 points. You use the old value, not the new value. Old value of u21, x3, this value and this value, this guy, and you compare. And after that you go to this point, and we will go along this direction. This is called the natural ordering. First you change x, then you y. That is called the natural sweeping direction. Okay, and in this way we will compute all the values. This is should be remember, this should be the main point. We do not use the new value of u11 in the calculation of u21 as soon as they are available. We use the old values of u's in the iteration loop. First I am just writing the algorithm for Jacobi iteration without in the part of the boundary values, only the main part of the calculation. First you have to initialize uij0 is 0 and ui is a temp, another variable where temporary variable for comparing is 0. For all interior points, I equals to n1 to nx minus 1 and j equals to 1 to ny minus 1. Now you start our iteration loop for all ij, compute uij temp in the temp for next n plus 1th iteration. That means n equals to 0 first iteration. That means 1/4 of ui plus 1j, all the old values. Now you compare, for suppose you run several times, if uij temp n plus 1th iteration value minus unij, that means the previous iterated value of the particular use, is less than 10 to the power minus some k is some convergent criterion based on, suppose k is 10 to the power minus 2, whatever it may be, 0.001 or whatever it may be, 0.000001, depending on the problems and your requirement. If two values in the first in the nth iteration and n plus iteration, the difference between these two values is less than some accuracy limit or just equals to, then we can exit the iteration. If not, this condition is convergence condition not met, not satisfied, then we go for, then we put the value of the temporary variable into the uinj value. Then we update the nth iteration value of all the u's. Now you go to step 2 for another sweep or another iteration, rather. Another iteration, you go all these things and you check this convergence criteria. If not met, you doing and doing until you reach this 10 to the power minus k. This is all about the Jacobi iteration.